Today I'm going to share with you some theory about correlation. The series is divided into three main videos, one on correlation, number two on hypothesis testing, and number three on using SPSS to calculate correlation. Correlation is a measure of central tendency, and we consider it a descriptive statistic because it's showing an interaction of two variables with each other in a direct mathematical relationship. There are a number of definitions for correlation. I'm going to share with you some of them. A measure of degree of association between two variables, and it varies between -1 and +1. A causal complementary parallel or reciprocal relationship, especially structural function or qualitative correspondence. Or an indication of strength and direction of a linear relationship between two random variables. Let's just make some meaning out of that. So, is there a pattern in the relationship between two variables? These are ways you can think about it. If a score on one variable is high, does the other one tend to be high? If one is low, does the other one tend to be low? Okay. And or the opposite relationship. If one is high, does the other tend to be low? And is there a pattern between that? So let's take this an example. Plot logical reasoning against creativity scores. So, is there a relationship between someone's logical reasoning skills and their creativity? You may say yes, you may say no, but you'd have to collect data to try to figure out. So, does there appear to be a relationship, and how would you describe it? I do want to say correlation is a very specific word. And in educational research and statistics, it has a very specific meaning. So sometimes people use the word correlation loosely. It is not to be used loosely when you're talking about the work we're doing in statistics and in educational research. So let's think about this reasoning. So let's take this. Let's say I had a number of people. They each did a logical reasoning assessment and they did a creativity assessment. So like if we look at this person right here who's got a score of 5 on logical reasoning and 7 on creativity, that's their point. We're plotting the relationship between the two, where they intersect with one another. And if you look at these relationships of this sample of about 20 people or so, you can see there generally tends to be, as logical reasoning increases, creativity increases as well. And what you need to do sometimes when you plot dots is imagine what you're actually seeing. So I can imagine a line of best fit that might run through here. It looks kind of one is going up and the other is going up with it as well. And so these are some of the types of correlations that may exist. So the one we just described, it's called a positive correlation. As one variable goes up, the other variable goes up. This and the value of the correlation would be somewhere between 0 and +1. Now, in the opposite relationship where something, this is called a negative correlation, as one thing goes up, the other goes down. That's a negative correlation. Now, that's okay. It doesn't mean anything bad necessarily, but those values are between -1 and 0. This is just a really well-developed positive correlation where it's mathematically very rich. So the correlation is a +1 in this case, and this one's a -1 in this case. These are pure values. It looks a little bit unlikely you'd ever have that experimentally. You get something more like this experimentally. Then at the bottom, we see this, the points are just kind of everywhere. So this is a no correlation situation where there's no correlation or no relationship. It's the lower it gets, the closer that value gets to 0, the least correlation there is. We call the calculation of the correlation the Pearson product moment correlation coefficient, mumbo jumbo for the letter R. So the Pearson R, it's sometimes called, and it's basically the relationship of the cross product of z-scores. So from our z-score section, we know those are standardized scores. And of course, that makes sense that correlation scores would be standardized because we want the correlation relationships to look the same. We always want them to be between -1 and +1. The only way we're going to do that is we convert everything to z-scores. So we use the standard scores rather than the Merck scores because of the difference in measurement. Now, This is just a formula I'm showing you of how it's calculated. You don't need to ever calculate this by hand. The computer is going to do that for you. What we want to think about, though, is this relationship here. If we're approaching 1, positive 1, a R value, a Pearson correlation or Pearson R of 1, we've got this positive relationship because as one goes up, the other one goes up in a proportional relationship to it. In a correlation, both variables are measured on at least interval scales, and for the Pearson moment product correlation. So we need interval level data to do this. That's typically how correlations are done. You can do correlations with ordinal level data, and it's a different formula that's used for that. But for the Pearson scale and the work we're going to be doing in this class, we'll be using interval scales to do Pearson R. The values are always going to be between -1 and +1. And the closer you are to 0, the less relationship exists. So if we think about 0 in the center, least relationship, and as we move positive and negative away from it and approach 1 or -1, we have a much richer, more precise correlation relationship. So ones, very high correlation. -1, very high correlation. Near 0, very little correlation or relationship. Okay, factors that you must take into consideration when you do this. The two variables must be paired with each other. So the same individual has to take both tests or assessments or whatever you're using to measure the two. And the Pearson relationship is looking at a linear relationship between the two variables. So there are other types of curves that exist. The linear relationship, you might remember from your algebra life, y equals mx plus b. That's what we're doing here. So this is a linear relationship because it goes up, but these are curvilinear relationships. This one looks kind of logistical in nature. This one's inverted as well. So these are not the kind of relationships we're going to be looking for in what we're doing here. We're going to be looking for these linear relationships up here. Now, let's keep in mind that correlation and causality are different things. Just because something has a high correlation doesn't mean there's causation for the variable. And we'll talk about it in a great example in a second. So the interpretation of causation is only appropriate if the variables provide a logical reason for interpretation. Okay, so let's give an example of that. There is a well-known positive correlation between ice cream sales and crime rates. As ice cream sales increase, violent crime almost matches ice cream sales identically over the course. And you can see the relationship plotted here. So here's the months of the year. We see ice cream sales are low in January and December, but they increase with a peak in July, August, and then decrease after that. And we can see violent crimes match it precisely. So is ice cream sales the cause of increased crime? Probably not. There's a correlation. It's not a causation. Like a third variable, like warm weather, might be responsible for the correlation. Warmer months, more people are outside. That increases ice cream sales. And it also increases the likelihood of social interactions, potential crimes, people outside. That would be the potential causation, which is different from the correlation. Okay. Now, the advice I always give is plot first, calculate second. If you plot first, you have a sense of what this looks like in advance, and you can start thinking conceptually in your mind, do I have a positive? Do I have a negative? How is the relationship going to be? So when we look at values, there are some rules we call the rules of thumb for correlation coefficients. If we see between 0.9 and 1, whether that be positive or negative, we see that's a very high relationship. Between 0.7 to 0.9, that's a high relationship. A moderate between 0.5 and 0.7, low relationship 0.3 to 0.5, and little, if any, relationship 0 to 0.3. What's interesting here is you can have significance, but the relationship be not super strong. On the wiki, I've shared this same information, the rules of thumb for interpreting excessive correlation coefficient. This might be a place you might go for additional information and resources. And as you learn more about correlation, you might consider making a contribution about it. This is the basis of correlation, the Pearson R, the relationship of two variables to one another. Do they form a linear relationship? Is that relationship positive or negative? And what magnitude or strength does that relationship exist? We'll look at these relationships in more depth now.